an undergraduate student here at the University of Toronto. He did his PhD with Harrison Seal from McMaster University. And now he's in the Netherlands at the European Space Agency. Today, Nathan is going to talk about collisional, small and body collisional dynamics. Thank you, Ferdy,
and thank you for having me. It's a pleasure to be back. Right, so I'll begin with a little historical background before getting into the present analysis. So the three-body problem was first considered by Newton in his Principia in 1687, and Newton was able to provide a qualitative description of something called Cauchy cycles, although he was never able to do anything quantitative with the problem. So I've sketched out here just a general, very rough picture of what Cauchy cycles are. So you're going to want to think about a hierarchical, stable triple system. So you have a close binary, and then an orbiting third companion. And the idea is, if you begin with a relatively large inclination between the inner and outer orbits, you can evolve to a state where the inclination is reduced, and this is obviously going to increase the total angular momentum of the system. So to compensate, the eccentricity of the inner binary is reduced effectively. So total angular momentum is conserved, and it's effectively just an internal evolution for stable triple systems. So Newton picked up qualitatively that this should occur. And this was really the first introduction to getting into the three-body problem. Later, it was picked up by several other big names, including Euler, Lagrange, Jacobi, Hill, and Poincaré. And in all cases, what these scientists wanted to do was they wanted to be able to predict the positions of all three bodies at any future time, given some arbitrary starting configuration. However, in all cases, the researchers had to make simplifying assumptions in order to make the problem tractable. So a good example is the coplanar restricted three-body problem. In this problem, well, first of all, you assume that all bodies are coplanar. And second, you assume that one of the three bodies is massless. So this reduces the number of unknown variables in your system of equations, and you can solve them exactly. Unfortunately, nobody ever arrived at an exact solution to the three-body problem. And after this, it was acknowledged that it's quite a challenge. And so a long period passed with relatively little progress until the late 1800s, when the King of Sweden, Oscar II, offered a prize to anybody who could solve the general three-body problem. And he stipulated that the solution had to be in the form of a deterministic series expansion that would provide the positions of all three bodies at any time, given any initial configuration. So it was in 1889 that the prize was given to Poincaré, who, although he did not solve the general three-body problem, it was said that he had made the most progress on the subject. And because of Poincaré, we know that a deterministic series expansion could never provide the desired solution, and the general three-body problem is an example of chaos in nature. Okay, so fast forward a few years. For Poincaré, a new approach began, namely integration of orbits step by step. So in this approach, you move each body forward incrementally, one at a time, and obviously this isn't correct, so it naturally introduces errors. However, the errors can be minimized by choosing appropriately small time steps. As you can imagine, this is a computationally expensive approach, and it was first attempted by Bureau in 1913, who considered a very specific example of the three-body problem. So I've shown that here. Turn the light for just 1 second. So in the Pythagorean three-body problem, the initial configuration is as follows. You make a right-angled triangle, and the vertices, the masses of the points, well, the masses are located at each of your three vertices, and you assign masses of 3, 4, and 5 in arbitrary units, and then the length of the sides correspond to the opposing vertex. And you start all bodies at rest, and you simply release them. And what Bureau found is he found first two bodies will undergo a close approach. They'll then have a close passage and recede. Another two bodies will undergo a close approach and recede. And this behavior continues. Bureau eventually reached the end of his calculated capacity, and this was before he actually got to the end of the Pythagorean problem. So it wasn't fully solved until computers came on the scene. And And as you can imagine, computers revolutionize things since they can perform the necessary calculations very, very quickly. And when computers were able to trace the Pythagorean problem to its conclusion, they found that what you're left with is one of the stars being ejected, so you have a binary and a single star. Okay, so despite the advantages offered by computers, very few studies have considered more than 3 bodies. The reasons being, there are long integration times to run the simulations to completion, and the integration times tend to increase as you include additional bodies. The parameter space that needs to be explored is extensive, and once again, as you include additional bodies, so as you go from the n equals 3 case, the 3-body problem, and you move to n equals 4, n equals 5, the parameter space grows rapidly. And finally, the number of possible outcomes increases steeply with n, where n is the number of objects that are interacting. So in the case of n equals 6, for example, if you take 2 stable hierarchical triple systems and you throw them at each other and let them interact, or let all 6 stars interact gravitationally in a very small volume, the total number of outcomes for this are well over 100, and this is without assigning numbers to the stars, so just generic outcomes. And this actually makes it quite difficult to neatly characterize studies. So for example, with a 3-body problem, you can describe the outcomes in terms of flybys, ionizations, exchanges. It's, so for example, you have 3 bodies, one comes in and it's swapped for one of the other bodies, which then leaves. Whereas when you have n equals 6, n equals 5, so on and so forth, things are much more complicated. Simply stipulating in terms of an exchange becomes more ambiguous since you need to specify which star was exchanged. All right, so before continuing, I'd like to show you a simulation of a dynamical interaction between a binary star and a stable triple system. This should give you an idea of what I'll be talking about, try to keep this general picture in your head. And what you should take away from this is that if you simply try to follow the evolution with the naked eye, and you were to, for example, count the number of close approaches that happen between stars, it can actually get quite ambiguous, and it's difficult to do with the naked eye. Whereas when you look at an interaction involving only 3 stars, it can be a lot easier to pick up general trends and characteristic behavior. So I'll show a little bit later another simulation of a single binary interaction, and in that case you'll see that you do get nice clean trends that you can use to your advantage. Okay, so there are a number of astrophysical applications for these types of dynamical interactions. Most of these happen in very dense regions, so places like the galactic center. There are some examples in young star-forming clusters, and dense star clusters like massive globular clusters in the outer reaches of the Milky Way. And these type of interactions are thought to be important for things like the formation of various types of stellar exotica. So these include blue stragglers, millisecond radio pulsars, low-mass X-ray binaries, even S-stars at the galactic center. You could form hypervelocity stars in this way, get tidal flares. Most of the examples I'll be talking about today happen in dense star clusters. However, at the end of the talk, I'd like to briefly go into some of the dynamical interactions that should be happening in young star-forming clusters, since I've got a new result that I'm actually quite excited about that I'd like to share. Okay, so getting to the motivation for the present study. So the current state of the observations is such that we've now identified triples in significant numbers in several moderately dense old open clusters. So these moderately dense old open clusters represent this intermediate regime between low sparse open clusters and massive dense globular clusters. So these guys tend to be on the order of a few gigayears old. They have central densities on the order of 100 solar masses per cubic parsec squared. And they tend to be dense enough that they're dynamically interesting. So dynamical interactions are thought to be happening relatively frequently and could be contributing to the formation of things like blue stragglers, millisecond radio pulsars. However, in these cases, the central densities are also sufficiently sparse that spectroscopy can be performed. So what this means is that people have been performing radio velocity surveys of these clusters for decades a little over 30 years now. And what they've been finding, actually relatively recently, since you have to look for a very long time in order to pick up triple stars, since the outer orbit tends to have a very long period, this means you have to look for a very long time in order to see the variations by radial velocity survey. What we're finding is that the fraction of stars in binary systems relative to the fraction of stars in triple systems, this ratio tends to be on the order of 5. So actually this was calculated using a study from 2007, and after speaking with the author of the study, since then, many of the binaries they've continually been observing the cluster where this calculation was done, and they found that a lot of the binaries have actually ended up being triple. So the number of triples has gone up, and the number of binaries has gone down. So this ratio is actually on the order of 4, and that's also what we see in the field of our galaxy. Okay, so I'll be arguing that triples should be undergoing encounters with other objects more than either single or binary stars, and that this is likely the dominant dynamical mechanism for stellar collisions to occur, at least in these moderately dense fold open clusters. So there are two characteristic features of stable triple stars in dense star clusters that I'd like you to keep in mind. The first of these is that the outer companion of the triple system tends to be on a very wide orbit. The average sub-major axis of this orbit is quite a bit greater than the average sub-major axis of a binary star. So this means that you've got a very wide cross-section for collision for triple stars, right? And a wide cross-section for collision obviously reduces the time that these things encounter other objects. The other property of triples that's important here is that in order for triples to remain dynamically stable for a very long time, you need a relatively large ratio between the sub-major axis of the inner orbit to that of the outer orbit. The reason being, you can imagine if you had a relatively small ratio, so the inner orbit is actually comparable to the outer orbit, the stars are too close, they'll interact, and the system will become unstable, and one of the stars will likely be ejected. So what this means is that stable triple systems tend to have a very close inner binary. Okay? And it's been shown by dynamical interactions of single binary encounters that the probability of a direct collision occurring between two stars increases dramatically as the sub-major axis of the binary is reduced. So if you're putting in very short period binaries in the dynamical interactions, this means the probability that a collision will happen between two of your objects becomes very high.
So does this ratio apply to open clusters?
It applies, so if you move to, I'll talk about that a little bit at the end. So if you, we really, there's, that I know of, we've been able to count the number of triple systems in relation to the number of binaries with reliable statistics in M67, Taurus Auriga, and the field. That's all that I currently, two clusters in the field. So it's something that I think the observations will see.
In global clusters, the density is much larger, so the number of tables will be much lower than the one in a open cluster.
So I'll come back on that and make a prediction for Bobby. Okay, so this plot is showing the parameter space in the binary fraction, triple fraction plane, for which each type of dynamical interactions dominates. So that is the parameter space for which each type of dynamical interaction occurs with the fastest rate. So when I'm talking about type of dynamical interaction, for example, 3 plus 3, this is an interaction between two triple star systems. 2 plus 3 is a dynamical interaction between a binary and a triple. 1 plus 3, a single star and a triple, so on and so forth. So the idea is that the observations are just getting to a point where we're being provided with observed binary fractions and triple fractions for individual star clusters. So if you're looking at a particular star cluster and you know the binary fraction and the triple fraction, this means you can place a point on this plot, and where the point falls, that tells you what type of encounter is occurring at the greatest rate. And so if we do this for the old open cluster M67, we find that our point falls right around here. So this is right at the intersection of single binary, 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 and single triple interactions. And so this is telling us that single binary, single triple, and binary binary interactions should all be occurring at roughly the same rate in this cluster. Now I mentioned that stable triples are pretty much always going to have a very wide cross-section, and they're also always going to bring in a relatively short period inner binary. And this is not going to be true for single binary and binary encounters, since the most likely encounters will involve two very wide objects or a single star and a very wide binary. So if they're occurring all at the same rate, these guys are going to be bringing in short period binaries the most, and therefore it's 1 plus 3 interactions that you would expect to be resulting in collisions more than any other type of interaction. And so just to be clear, when I say collision, I mean 1 plus 3 is an interaction involving 4 stars, and I'm talking about only 2 of those objects meeting, colliding directly, and making one new object or a new star.
So for every one of these regions, there's a chance of there being some number of interactions that are like 2 plus 2 area. You still can get 3 plus 3 interactions.
Right. It just means 2 plus 2 are happening more often.
There's relative numbers.
Yes. Yeah. Exactly.
So how much?
So I'll come into that a little bit at the end, but it depends on. So to make this plot, I had to make one assumption, namely the ratio between. So I have to assume that all binaries and all triples have the same cross section, and I have to choose a ratio between the semi-major axis of a binary and the semi-major axis of the other orbit of a triple.
What are the semi-major axis?
Sorry?
What are the semi-major axis?
The average semi-major axis?
Yeah.
So for the binaries, I think it was on the order of 5 maybe. So it's been a while since I've done this calculation, but I calculated the average binary semi-major axis for the open cluster NGC88, which is very, very similar to M67, and it's the only open cluster that we have reliable period distributions have been derived. And then I assumed a ratio between the average triple semi-major axis and the average binary semi-major axis, and I chose a ratio of 5, since it should be a relatively good volume limit. I wanted to choose, or be as conservative as possible when choosing that ratio to get a feel for how important triples could be, so I obviously don't want to favor triples when trying to establish whether or not they can work well. Okay, so getting to the problem at hand, effectively we want to test the preceding hypothesis that collision should be happening in interactions involving triples more than any other type of interaction. In particular, we want to address the question, how does the probability of a collision occurring depend on the number of objects involved in the interaction? Or what is the n dependence, where again, n is the number of objects involved in the interaction? So the motivation here is that in principle, if we want to take some of the tricks and trends that have been identified for the 3-body problem and extend them to interactions involving more objects, we need to quantify how the outcomes depend on the number of objects involved in the interaction. Okay, so I'll just very briefly go over the method I'm going to lay out to do this and to extract the n dependence. Basically, we're going to formulate an analytic prediction for the collision probability, and then we're going to test it and compare it to the results of numerical scattering experiments, which are just computer simulations where we throw 2 triples at each other, a triple and a binary, so on and so forth, and go through and do millions of these interactions and calculate how many of them actually result in a collision. So the first thing we have to do when we want to compare between different encounter types, so encounters involving different numbers of objects, is to find some sort of normalization. So what I'm talking about here is that there's actually a few parameters that affect the outcomes of these interactions. And if we want to be able to get at the n dependence, we effectively have to remove those other dependencies in order to isolate the dependence on the number of objects involved in the interaction. So we're going to do some normalization where these other parameters are going to be the same for all of our types of interactions, and the only thing that's going to be different between them is the number of objects. Once we've done this, we can choose our initial conditions. We can then perform our scattering experiments, and we'll then compare them to our analytic prediction for the collision probability and extract the n dependence. Okay, so going into the normalization in a little more detail. So previous experiments of single binary interactions and binary-binary interactions have shown that the two most important quantities affecting the outcomes of these dynamical interactions are the total energy and the total angular momentum. Okay, so what this means is that when we're comparing different types of encounters involving different numbers of objects, we need to be comparing encounters that have the same total energy and the same total angular momentum. So our normalization is simply that we fix the total energy and the total angular momentum when comparing between different types of encounters. And I'll show that a little bit more on the next slide here. So I've divided things into 3 runs. Each run has a different choice of initial conditions, and the initial conditions are decided by the 7 major axes of the binaries and the orbits and the triples. And so the idea is, so if we focus on run 1 here, okay, what we've done is for this particular run, this is normalized. So the total energy and total angular momentum for all of these different encounter types are fixed for run 1. So the only difference between these types of encounters are the number of objects involved in the interactions. So long as we're comparing encounter types solely within run 1, we're safe to extract the independence. We'll then do it again for run 2, for run 3, for different choices of the total energy and total angular momentum, and make sure that whatever we find for the independence is not sensitive to this fixed ratio between energy and angular momentum. So for these, as I mentioned, the parameter space can be extensive, so we chose to focus on all equal mass objects, so all 1 solar mass stars. We varied the relative velocities between objects from velocities of 0 to critical velocity. And the critical velocity is a useful quantity to define these scattering experiments, since it's the velocity for the system, the relative velocity between 2 objects that gives you a total energy of 0. Okay? So basically, if you go above this critical velocity, you've got a positive energy, and this means that you're very likely to get complete ionization for the system. You're putting in a lot of energy, so it's likely that if you throw 6 objects at each other, they can easily all leave as 6 single stars. Whereas if you have a very negative total energy for the system, you're much more likely to end up with things still bound. Right? So 2 triples or 3 binaries or something like this. We also varied the impact parameter. So this is, you just want to think of the impact parameter as how directly you throw 2 objects at each other. So an impact parameter of 0, you're throwing them directly at each other. If an arbitrary units, an impact parameter of 1 means you're throwing it a little off the center, 2 even farther, 3, so on and so forth. And we choose the impact parameter simply as the geometrical cross-section for collision, and we try a few different impact parameters going at a few times the 7 major axes. Okay, so we then performed our scattering experiments. To do this, we used the few-body numerical scattering code. So this was designed to handle encounters between single stars and binaries. So we upgraded it to handle encounters involving triple stars. We're going to make these new subroutines available on the few-body webpage, so if anybody's interested in performing scattering experiments with triples, shoot me an email since it's not available quite yet, but it'll be up with the new version of few-body shortly. Now we have to focus on the low angular momentum regime. Well, we don't have to, but we do. The reason being, again, parameter space is extensive, so we have to choose some regime to focus our energy on. And it's beneficial to look at low angular momentum because the integration times for low angular momentum tend to be shorter than the integration times for higher angular momentum. So effectively, higher angular momentum encounters tend to last longer, so you're integrating the encounter for a long period of time, and if you're performing millions of scattering experiments, this can add up. So focusing on the low angular momentum regime allowed us to maximize the number of encounters we could, or number of simulations we could actually perform. So for every set of different initial conditions, we performed 800,000 simulations for every encounter type. So in total, we performed something like 15 million simulations, and this was necessary in order to get good sampling and statistically reliable results. The reason being that we varied relative inclinations between inner and outer orbits of the triples, as well as the phases and relative inclinations between orbits of encountering objects randomly. So we need to perform a lot of objects in order to properly sample that parameter space. And once we performed all of our different scattering experiments for a given run, we then, for every encounter type, simply count the number of encounters that result in a direct collision between two objects, and divide by the total number of encounters performed, and this gives us the collision probability, which we can compare directly to our analytic model. So a collision. So a collision is when two stars directly smash into each other and they form a new star. So they're going to merge, basically.
In your algorithm, how is a collision defined?
So few body, it gives finite sizes for the stars. So it's purely defined as whenever the stellar radii overlap. Yeah, 6 star.
Do they all have some stars?
Yeah, they all have. So we chose one solar mass stars, we chose one solar radius with their cross section. So actually, we're really focusing on one collision here, but if you focus on, we've done a little bit looking at the probability of 2 collisions happening during the same interaction, and they're actually the collision product is actually expected to expand. You can expand by a factor of several, so 3 to 10 or something like this. Just think about like you've got 2 stars interacting each other with some positive kinetic energy, and it goes into the stars, so it just kind of puffs them up, right? And then they'll eventually shrink back down by radiating away the energy. But for a relatively prolonged period of time, you have a loaded object, which obviously has a larger cross section, and that's going to help it encounter other objects. Okay, so the next thing I'm going to talk about is I'm going to explain how we got at the analytic formula to predict the collision probability that we compared to our numerical scattering experiments. However, first I want to show you another simulation courtesy of Aaron Geller, this time of a single binary interaction. And there are some characteristic behaviors to note here. So first, the system tends to evolve by forming a temporary binary that experiences a series of interactions with the other remaining single star. And these can be described as a series of ejections that take place until eventually an escape occurs. And one of the stars becomes unbound from the system and leaves behind a single star and a binary. And this characteristic behavior, so some of these ejections tend to be relatively long-lasting, some are a relatively short duration. But the characteristic behavior is the same every time, more or less. And so some of these trends are the temporary binary generally has a semi-major axis that is half that of the binary originally going into the interaction. The components of a temporary binary experience on average 2 close approaches per crossing time. So these are 2 trends that will come in quite helpful for laying down this analytic prediction for the collision probability. So these trends allowed previous researchers to identify an analytic formula for the probability of 2 objects colliding during a given single binary interaction. And so they showed that the probability is effectively proportional to the average number of close approaches per crossing time multiplied by the total number of crossing times the system survives. So you want to think of that as the average number of close approaches per unit time interval multiplied by the total time the system survives for, right? And they show that this actually gives you a relatively good prediction for the collision probability that matches what you get out of these numerical scattering experiments relatively well. So we exploited this and tried to generalize it by including a general n dependence. And so that appears here. So we've included a power law index on n, the number of objects involved in the interaction. And when we fit this general functional form to the results of our scattering experiments, we're going to try to extract this n dependence beta parameter, and that'll tell us what the power law index on n is. A couple other points of note. So a good example of how those trends tie into this equation. So Q here, Q is the distance of closest approach between 2 objects. So for a collision, that is simply defined as the stellar is the radius of an object, right, the size. A naught is the semi-major axis of the binary initially going into the interaction. So I mentioned that the temporary binary that gets formed generally has a semi-major axis that's half that of the original semi-major axis of the binary going into the interaction. So knowing the original semi-major axis of the binary, we know roughly what the semi-major axis of the temporary binary is, and we can write down the ratio of the average size of an object to effectively the average interaction size of the region. You can imagine that if you've got very big objects in a very small interacting region, then the collision probability is going to be very high, whereas if you've got very small objects interacting over very large volume, it's not too probable that two objects are going to meet on the plot. Okay, so we're going to fit this function to the results of our scattering experiments and obtain the best fit parameters. And this is what we get when we do this. So this is what we find for run 1. So on the x-axis here, we have total angular momentum, which you really just want to think of as the impact parameter. So down here, we're throwing objects directly at each other, whereas way up here, we're throwing them not at all directly at each other. On the y-axis here, we have the probability of a single collision occurring between two objects. The open stars are triple-triple interactions. The solid triangles are binary triple. The open circles are single-triple. The solid circles are binary-binary. So you see that for n equals 4, the single-triple and the binary-binary, they agree quite well. And then down here, the crosses are single binary interactions. So a few points of note. First, the collision probability increases with increasing n. So we see for n equals 6, the probability is in general higher for n equals 5, and this is higher than it is for n equals 4. We also see an exponential drop-off with increasing angular momentum, and this drop-off seems to be a little steeper for larger n. And this obviously makes sense, since you would naturally expect that you're most likely to have two objects collide when you throw them directly at each other, whereas you're least likely to have two objects collide when you throw them very far apart.
It seems, maybe you're wrong, but it seems like same energy, angular momentum, same impact parameter, same all the parameters you talked about. Just the phase of where, sort of for a binary, like where they start in the orbits both, each individual, you can fix all the parameters you talk about and do it a bunch of times and still get different answers. Just because it seems chaotic, right? I mean, so you start off here where they're orbiting, and you start off in those, and you start off like that instead. And you just keep doing that for all the particular.
So one thing people have shown is that the outcome is really, really sensitive to how you start those relative. So you have no right to expect that you should get out a consistent beta parameter then, if that is if it. I shouldn't find it. So what you're saying is I should not find the same beta parameter for every run.
Yeah, you would seem to have to do ensembles of basically initial conditions, fixing all the other parameters.
You mean run through every possible parameter for a given run? Or maybe we can talk about
yeah.
that later. Okay.
That is
what it's doing.
Maybe I'm misunderstanding something. Yeah.
Okay, but we actually, so we vary all those relative phases and inclinations over, that's why we have our millions of scattering
Oh,
experiments.
okay, I didn't get that part.
Because we could probably sample that.
Okay, I understand.
So other than
Yeah, everything's random.
Okay, so each, okay.
the points, are those error bars? Or?
Yeah, these are actually error bars here. So the errors are just root n plus all sophistics, which is formally not quite correct for numerical scattering experiment. You need to include unresolved encounters in the error, but they are a very small fraction of scatter. Sorry?
That's sort of the scatter you get for all the different possibilities.
Yeah, so we actually, we included an intrinsic dispersion when doing the fit, so In order to get a reduced chi-squared of 1, we actually increase the size of the errors by a fixed factor for all errors, and we end up with our error bars that are more like something like this in the end, which we felt personally were more reflective of formally gives you chi-squared.
One of the points is the 800,000 simulations to that,
So there's 800,000 simulations for this one, 800,000 for this one, 800,000 for each one. So in total, yeah, you get 4 million.
Yeah.
Okay, so when we extract our beta parameter, we find that we get a power law index of 2 to within roughly 2 standard deviations for all of our runs. So I've got here 3 primary runs where we perform 4 million simulations in total. However, we also conduct an additional, I think, 8 runs in total, varying the ratio between the energy and the angular momentum to test the robustness of the beta parameter that we found, and we find consistently a beta parameter relatively close to 2. Tends to range by a little bit less than 2 to, and in a handful of cases, it could actually get up close to 3, but these seem to be coming for higher angular momentum encounters, and we expect naively that this is where our normalization should actually start breaking down. So this was another part of the design focused on the low angular momentum regime. However, this beta equals 2 seems to be robust. So I'm not going to go into too many of the nitty-gritty details here of the mechanics of why you get this beta equals 2, since I can't formally give you an answer that convincingly shows you where it's coming from. However, one interesting point is that if you simply think about the mean free path approximation and the collision rate that you get from it, that collision rate scales as n squared, right? Where the collision rate is simply the average time any 2 objects should experience an encounter. So you naturally get this n squared dependence in the limit of very large n. Okay? So we've shown that as you go to very small n, this n squared dependence is actually maintained. So it's perhaps not terribly surprising that you get a power law index of 2. And personally, I'm inclined to think it's not a coincidence. I think you can explain it simply by the fact that you would expect n squared branching ratios available, right? So if you just think about the probability of any 2 objects colliding, you have more objects, so that you can just, the number of ways that you can randomly combine 2 objects is higher for n equals 6 than it is for scales as n squared. But I'd like to show that. So that would be future work. Next, I'd like to actually step back from talking about collisions happening during these interactions and talk about some ongoing or work in progress we've been doing. So here, I'm going to talk about what was asked about earlier, which is what fraction of your interactions give you different types of outcomes. So you're going to want to think about the fraction of interactions that will leave you with a binary and triple, or 3 binary stars, or 6 single stars, so on and so forth. In particular, we want to address the question, how can you distinguish between primordial versus dynamically processed populations of binaries and triples and clusters? So let's say you're looking at a star cluster in our galaxy, and you're looking at the binary and the triple populations, and you want to know, have these been dynamically processed at all? Have these been affected by dynamical interactions, or are we looking at the binary and triple populations that the cluster was born with? And to address this question, I'm going to use 2 example clusters. So on the left here, we have the young star-forming region, Taurus Aurora. So Taurus has an age of on the order of 1 million years. It has a density on the order of 1 solar mass per cubic parsec. And if you calculate the average time for any 2 objects to experience a collision, and you compare it to the age of the system, what you find is that the time scale for collisions is much, much longer than the age of the cluster. So this suggests that you would expect that a cluster like Taurus Aurora should be relatively unaffected by dynamics. Okay, so we're looking at the binaries and the triples in this cluster. It should be, in principle, fair to assume that those are the binary and triples that the cluster was born with. Okay? They have not yet been affected by dynamics. Now, if we look at an older, denser, and more evolved cluster, namely M67, And so this guy's got an age of about 4 years. He's our template example of these intermediate open clusters, this intermediate case between sparse open clusters and massive dense globulars. If we compare the age of this system to its collision time, we find that the collision time is much shorter than the age. So in this cluster, we would expect the binary and triple stars we see to have been relatively affected by dynamics. Okay, so we do not think that the binary and triple populations in this cluster are primordial. Right? How can we check this? Okay, so I mentioned that the observations are at a point where we still don't have a lot of, in particular, triple fractions for clusters. But we have them for Taurus Auregae and M67, so we can put points down on our plot, and we find that in Taurus, binary triple interactions should currently be dominating, whereas we showed earlier that in M67, it's single triple. And what we want to know is, is this more primordial than this guy here, or is it the other way around? Is there any way that we can actually provide some sort of dynamical age dating? And the answer is, it looks like we can. So what I've done here, basically I populated the plot with a bunch of initial binary and triple fractions, so where these arrows start here, and I asked, as all these different types of interactions occur, so as you have triples encountering triples, triples encountering binaries, and single stars, and so on and so forth, the dynamical processing is happening. How does the binary fraction and triple fraction combination evolve? And what you see, so this plot is not perfect. It's a work in progress. In particular, ignore down here, since this part of the plot isn't right, and focus on this part. We see these nice curves, or what will be nice curves when this is all redone with n-body models, that kind of come in along here, and they seem to converge towards a common evolutionary line that's pointing this way and to the origin. So I mentioned, first of all, M67, so this is done with the observations from 2007. Since then, binaries have been identified as actually being triples. So this point should move up and to the left here. We're not sure how far up and to the left it should go. Taurus Auregae, on the other hand, is probably in roughly the right spot. And the key point to take away is that if you start in the position that Taurus Auregae is at, you can evolve dynamically to where M67 should be. However, the opposite is not true. So you could not start with the binary and triple fractions in M67 and end up with the binary and triple fractions in Taurus Auregae. So this is giving us relative age dating. So it's telling us that a cluster like M67 is consistent with being dynamically older than Taurus Auregae is. And actually, so what the bottom right of the plot should look like is you should get these nice arrows that actually come up and curve in as well. So this portion of the plot should actually be analogous to this portion. And you should have a series of lines, or parabolic lines, all coming in and converging towards this one line of common evolution pointing towards the origin.
Why should you make more triples before you make less than?
Sorry?
Why should you make more triples before you make less than?
Because binary interactions, if you throw two binaries at each other, they're going to give you, it's not uncommon they'll make a stable triple. So that's actually not included here, and that's why it shoots towards the origin so rapidly, and it actually shifts it off a little bit first.
I thought that tau was a very hypergraphic case, right? It's a very low density cluster. I was wondering what would happen if you actually put a more standard cluster of
So I'd like to, I think. So one interesting thing is if you put the field down, or the ratio of binaries to triples to the field, it ends up being right around somewhere in here. And so I mean, there's this idea that most of the stars in the field actually come from star clusters that have dissolved. And if that's true, then you might expect the binary and triple populations in the field to have actually been processed dynamically in star clusters at some point long ago. And so if this is true and all binaries and triples were actually processed dynamically in clusters before escaping into the field, then that can explain why the ratio is fixed at a more dynamically evolved ratio between the binary and triple fractions than something like Taurus Auregae. And it also predicts that if you could go out and measure the triple fractions in globular clusters, you're predicting that they should be somewhere around here. And at least with the binary fractions, that is consistent with what we've measured for binary fractions in globulars. We see very low binary fractions in globular clusters with the highest collisions. So there's this anti-correlation basically between the mass of a cluster and the binary fraction, which is the same thing as saying there's an anti-correlation between the binary fraction and the collision rate, since collision rate scales with total mass of the cluster. Yeah, so that's some work in progress I've been quite excited by. And just to summarize, so we presented a new formalism to quantify the dependence of the collision probability on a number of objects. So short encounter times plus high collision probabilities suggest that triples should be the main channel for collisions in at least the old open clusters I've been discussing. And by extension, triples can be important catalysts for the formation of stellar exotica. So things like loose stragglers, low mass X-ray binaries. And we really need to be factoring in the importance of triples dynamically when looking at these types of objects in dense star clusters, the galactic center, so on and so forth. And we've shown how the observed binary and triple fractions can be used to constrain the relative dynamical agents of star clusters. And that's it. Questions?
Is there a Markov stable value in that plane? Like, you have transition, relative transition matrix. Does it converge to just a very small fraction of?
That seems to be, I think, yeah, that looks like what it's going to do. So that line is basically converging towards binary and triple fractions close to zero.
When you take that rate matrix and find the Markov stable vector?
You've lost me a little bit already. I feel like.
Oh, I mean, you just ask what's the vector that you apply the
Okay.
rate to? You get the same vector out.
Okay.
Just wondering if that's exactly zero or if that's.
I don't know yet.
Some very small number.
I think it's a very small number. So I would argue that the important quantity is the hard-soft boundary cluster. So I'm not sure if anybody's familiar with Peggy's law, but it's this really elegant result that you can divide binaries into, you classify them as either hard or soft. And the general picture, you can, if you just take the average kinetic energy of a single star in the cluster. So, or sigma naught, we'll focus on the central cluster region. So, sigma naught here is the central velocities version, three-dimensional velocities version. And you set it equal to the average binary energy of a binary, and you solve for the 7-meter axis. You'll find that it depends on your velocity dispersion and the average stellar mass. That's it. So basically, you get to this regime where if your 7-meter axis, this gives you some critical 7-meter axis basically. And if your 7-meter axis is smaller than the critical 7-meter axis, it means that your binary is hard. Whereas if it's larger, it means your binary is soft. And you can make this general statement that when soft binaries undergo encounters in clusters, they end up being destroyed, whereas when hard binaries undergo encounters in clusters, they just tend to get harder. So basically, hard binaries remain binaries, soft binaries are destroyed. And this critical 7-meter axis goes down as the collision rate goes up, or the mass of the cluster goes up. So you can imagine that if you have a smaller critical 7-meter axis, it's going to make it a lot easier to break up a larger fraction of your binary population. And so this is why you get an anti-correlation between binary fraction and collision rate, right? It just so happens that the guys experiencing the most collisions also have the smallest critical 7-meter axes. And so most binaries are going to be destroyed, and the only ones that survive in those cases are the very tight, close-inner binaries. So I think that. So I think that's part of why you're going to very low binary and triple fractions when you get to these very massive clusters with high collision rates, basically. but you shouldn't go to 0.
Another question? And it would be cookie substance. Let's thank Nathan again.